The boundedness property, let f be continuous on the interval ab, closed bounded interval, then 1. F is bounded on ab, and 2. F attains both a maximum value and a minimum value somewhere on ab. Commentary. Part 1 of this result claims that there exist real numbers m and m, such that f of x lies between both of these values, for all x in ab. So there's the boundedness property there. Part 2 makes the stronger claim that f attains both a maximum value and a minimum value on AB. In other words, that there exists a C and D in AB such that f of x lies between these two values for all x in AB. And it actually, f of x will equal f of c when at the point C and also at the point D here. So it attains those values. So let's just sketch that then. Let's do a quick sketch here. So we've got an axis then, and we'll draw a function. We'll go from A to B and just try and highlight what it means. So we've got a function defined on AB then. So let's do one. There it is there. So what have we got then? Okay, so f is bounded, so if you've got a continuous function on the interval ab, then f is bounded on AC, so we can see if we can take this uppermost value here. We'll call that capital M according to the notation. Take this value here. This is lowercase m here. Okay, so f attains both a maximum value. This value was attained near the endpoint, down here. So we can call that point D, and the minimum value, on this example it's here, we can label that C. So it says f attains both a maximum value and a minimum value somewhere on AB. So basically, in other words, that there exists a C and a D in AB such that f of C is the lowest point and f of D is the biggest point. So f of x will lie between those for all x in A and D. So the preliminary observation now, let's have a quick look at this one then. Here's the preliminary observation. Let's do this little part then. Okay, so the proof of 1 requires the key observation that if f is a function, f is continuous at C. If f is a function, is continuous at C, then f is bounded on the interval here, C minus delta to C plus delta, for some delta greater than naught. This can be deduced from the epsilon delta definition of continuity, which states that for every epsilon there exists a delta such that if this holds, then this holds. By letting epsilon equal to 1, other values of epsilon could equally well be chosen. For this value of epsilon, there is a delta then, greater than naught, such that if this holds, then this will hold, won't it? Triangle inequality. So f of x itself, add the 0 here. The 0 we're going to add is minus fc plus fc. So if we imagine that in our mind's eye in here, beside the f of x, then we use the triangle inequality, less than or equal to, so basically here's your f of x, add the 0 is here. So it's less than or equal to the first modulus by the triangle inequality plus the modulus of the second here. And then we know that this is less than 1, so this whole sum then will be less than 1 plus modulus f of c. In other words, f of x's are bounded by this value on this interval. And here's the interval here. Because this inequality is none other than just x is less than c plus delta and is greater than c minus delta. X lies within a distance delta of c. X lies within a distance delta of c, isn't it? This argument can easily be adapted to show that since f is right continuous at A and f is bounded on the interval, f is bounded on the interval of the form A plus A delta dashed with some delta dashed greater than naught. So let's have a quick look at proving that then on this initial section. So we got right continuity, and then we want to show if we got right continuity that f is bounded on that on a segment. So let's do the same again then. Let's take epsilon greater than or equal to 1 again. This suffices, any positive value should do really. So here we know for right continuity, if at a, isn't it? So if a is less than x is less than, so for every epsilon there exists a delta dashed, we'll call it, greater than 0, such that when x lies in here, just to the right of a within a distance delta, then we know that the f of x is minus the limit f of c, f of a in this case, isn't it, is less than epsilon, which is 1. Okay, so in this section then we do exactly the same as what we did over here. The f modulus of f of x then. If this holds, then we look at the f of x's. We have this inequality here. So this will be less than or equal to f of x minus f of c, or f of a now, would be 1. And this would be f of c would be f of a, wouldn't it? 1 plus f of a. Okay, so we know it's less than because this is less than 1, so this would be, this sum here would be less than 1, so we can get rid of that less than or equal to that I decided to write. There we are, that's better. Okay, so there's f of x, i.e. f of x is bounded. So I think we can see that in our mind's eye, more or less. I've just penciled in the is bounded, or in other words, f of f itself is bounded, isn't it? A function. That's it. Okay, good. So this is this part of the section. In the next section, we'll go on to the part 1 proof.